calculating ampacity for a duplex versus two dwelling units using Article 220.33 of the National Electrical Code, or NEC, involves a few key steps. It's all about determining the service load for each unit and then applying the appropriate calculation methods. Firstly, you need to calculate the service load for each dwelling unit in the duplex and for the two separate dwelling units. This calculation should be done using the applicable load calculation method, such as NEC 220.82. This section of the code provides guidance on optional feeder and service load calculations for dwelling units. The goal is to determine the maximum demand that each unit is likely to place on the electrical system. Secondly, you need to calculate ampacity for the duplex using Article 220.33. For a duplex, the ampacity for the feeder and service conductors can be calculated using Article 220.33. This article provides specific guidelines for calculating the load on a feeder or service where two dwelling units are supplied by a single feeder or service. This calculation typically allows for some demand factors that recognize the likelihood that not all loads in both units will be operating at their maximum simultaneously. When calculating the feeder ampacity for the duplex using Article 220.33, you'll use 125% of the maximum non-continuous load, which often includes lighting, plus 100% of the continuous load, which encompasses all other loads. Continuous loads are those expected to operate for 3 hours or more. For the service ampacity, you'll take 125% of the feeder ampacity calculated in the previous step. This provides an additional safety factor to ensure the service conductors can handle the load. Thirdly, you'll want to calculate ampacity for two dwelling units with Article 220.33. For two separate dwelling units, the ampacity for the feeders and service conductors must be calculated in accordance with NEC 220.82 without applying the provisions of Article 220.33. This means you treat each dwelling unit as a separate entity and calculate its load individually. For a feeder ampacity, you'll use 100% of the maximum demand load for each unit. This is a more conservative approach than using Article 220.33, as it doesn't allow for any demand factors between the two units. Similar to the duplex calculation, the service ampacity is 125% of the feeder ampacity. This ensures the service conductors are adequately sized for the combined load of both dwelling units. Fourthly, you need to compare ampacities. You should compare the ampacity values calculated for the duplex using Article 220.33 to the ampacity values calculated for the two separate dwelling units without using Article 220.33. This comparison will determine whether the duplex can be supplied with a low ampacity feeder and service. In conclusion, if the ampacity values for the duplex using Article 220.33 are lower than those calculated for the two separate dwelling units without using Article 220.33, then the duplex can be supplied with a lower ampacity feeder and service. This is because Article 220.33 allows for some demand factors that reduce the overall calculated load. Conversely, if the ampacity values for the duplex using Article 220.33 are higher or equal to those calculated for the two separate dwelling units without using Article 220.33, then the duplex must be supplied with the same or higher ampacity feeder and service as would be required for the two separate dwelling units. This ensures that the electrical system is adequately sized to handle the load, regardless of whether the dwelling units are combined in a duplex or separate. To further illustrate this process, let's consider a practical example. Suppose we have a duplex and two separate dwelling units, each with a similar load profile. This load profile includes lighting, general receptacle outlets, electric heating, air conditioning, and an electric range. We'll use the optional calculation method outlined in NEC 220.82 to determine the demand load for each unit. Let's assume that after applying the demand factors in 220.82, we find that each dwelling unit has a demand load of 100 amps. For the duplex, we can apply Article 220.33. This article allows us to consider that not all loads in both units will be operating at their maximum simultaneously. After applying the appropriate demand factors from Article 220.33, let's say we arrive at a total demand load of 160 amps for the duplex. The feeder ampacity would then be calculated as 125% of the non-continuous load plus 100% of the continuous load. Assuming the non-continuous load is 60 amps and the continuous load is 100 amps, the feeder ampacity would be 1.25 * 60 plus 100 equals 175 amps. The service ampacity would be 125% of the feeder ampacity, which is 1.25 * 175 equals 218.75 amps. We would round this up to the next standard size, which might be 225 amps. For the two separate dwelling units, we calculate the load for each unit individually with that applying Article 220.33. Since each unit has a demand load of 100 amps, the total demand load for both units is 200 amps. The feeder ampacity for each unit is 100 amps. The service ampacity is 125% of the feeder ampacity, which is 1.25 * 100 equals 125 amps for each unit. However, since the service conductors supply both units, we need to consider the total load. In this case, we would typically size the service conductors to handle at least the sum of the individual unit loads, which is 200 amps. The service ampacity would then be 125% of 200 amps, which is 250 amps. Comparing the results, we see that the duplex, using Article 220.33, requires a service ampacity of 225 amps, while the two separate dwelling units require a service ampacity of 250 amps. In this scenario, the duplex can be supplied with a lower ampacity feeder and service due to the application of Article 220.33. However, it's important to note that this is just an example, and the actual ampacity values will depend on the specific load profiles of the dwelling units and the applicable demand factors. Always consult the NEC and local codes for accurate calculations and to ensure compliance with electrical safety standards. It is also important to consider future expansion when sizing your service. While the NEC provides methods for calculating the minimum required ampacity, it is often prudent to size the service conductors and equipment to accommodate future load growth. This can save you money and hassle in the long run by avoiding the need to upgrade the service later. Another important consideration is the voltage drop. Voltage drop occurs when the voltage at the end of a conductor is less than the voltage at the source. Excessive voltage drop can cause appliances and equipment to operate inefficiently or even fail. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. When calculating the required conductor size, be sure to account for voltage drop to ensure that the voltage at the dwelling units is within acceptable limits. In addition to the NEC, local codes and regulations may also apply. These codes may have more stringent requirements than the NEC, so it is important to be familiar with them. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system is properly designed and installed. Safety is paramount when working with electricity. Always to energize circuits before working on them and follow proper safety procedures. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. Furthermore, consider the impact of energy efficiency when performing load calculations and sizing electrical equipment. Energy-efficient appliances and lighting can significantly reduce the overall load on the electrical system, which can lead to lower energy bills and a smaller carbon footprint. When selecting appliances and lighting, look for the Energy Star label, which indicates that the product meets certain energy efficiency standards. Also, consider using LED lighting, which is much more energy efficient than traditional incandescent or fluorescent lighting. In addition to energy efficiency, consider the impact of renewable energy sources. Solar panels, for example, can generate electricity and reduce the load on the grid. If you are considering installing solar panels, be sure to consult with a qualified solar installer to determine the appropriate size and configuration for your needs. Also, be aware of any local regulations or incentives that may apply to solar installations. Grounding and bonding are also critical aspects of electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to protect people from electric shock. Bonding connects all metal parts of the electrical system together, which helps to equalize the voltage and reduce the risk of shock. The NEC has specific requirements for grounding and bonding, so be sure to follow them carefully. Surge protection is another important consideration. Surges are sudden increases in voltage that can damage or destroy electronic equipment. Surge protection devices, or SPDs, can help to protect your equipment from surges. The SPDs should be installed at the service entrance and at any sensitive electronic equipment. Arc fault circuit interrupters, or ASIs, are another important safety device. ASIs detect arc faults, which are a common cause of electrical fires. ASIs should be installed on branch circuits that supply bedrooms, living rooms, and other areas where people are likely to be sleeping or spending time. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs detect ground faults, which can cause electric shock. GFCIs should be installed on branch circuits that supply bathrooms, kitchens, and other areas where water is present. Electrical inspections are an important part of ensuring electrical safety. Most jurisdictions require electrical inspections for new construction, renovations, and repairs. Electrical inspectors will check to make sure that the electrical system is installed correctly and that it meets the requirements of the NEC and local codes. Permits are often required for electrical work. Permits help to ensure that the work is done safely and in accordance with code. Contact your local building department to determine whether a permit is required for your electrical work. Proper labeling of electrical panels and circuits is essential for safety and troubleshooting. Each circuit breaker should be labeled with a description of the equipment or area that it supplies. This will help you to quickly identify and energize the correct circuit when performing maintenance or repairs. Regular maintenance of your electrical system is important for safety and reliability. Check your circuit breakers and GFCIs periodically to make sure they are working properly. Inspect your wiring for any signs of damage or deterioration. If you find any problems, have them repaired by a qualified electrician. When working with electricity, always use the proper tools and equipment. Use insulated tools to protect yourself from electric shock. Wear safety glasses to protect your eyes from sparks and debris. Use a voltage tester to verify that circuits are de-energized before working on them. Never work on electrical equipment when you are wet or standing in water. This increases the risk of electric shock. If you are not comfortable working with electricity, hire a qualified electrician to do the work for you. Electricity can be dangerous, and it is important to take precautions to protect yourself and your family. Furthermore, understanding the concept of demand factors is crucial for accurate load calculations. Demand factors are multipliers that are applied to the connected load to estimate the maximum demand that the electrical system is likely to experience. These factors take into account the fact that not all loads will be operating at their maximum simultaneously. Demand factors vary depending on the type of load and the number of appliances or equipment connected to the circuit. The NEC provides tables of demand factors for various types of loads. These tables should be consulted when performing load calculations. For example, the NEC provides demand factors for electric ranges, electric dryers, and air conditioners. These factors recognize that these appliances are not likely to be operating at their maximum capacity all the time. By applying the appropriate demand factors, you can avoid oversizing the electrical system, which can save you money on materials and installation costs. It's also essential to understand the difference between continuous and non-continuous loads. Continuous loads are those that are expected to operate for 3 hours or more. Non-continuous loads are those that are not expected to operate for 3 hours or more. The NEC requires that continuous loads be calculated at 125% of their nameplate rating. This is to account for the fact that continuous loads can cause conductors and equipment to overheat. Non-continuous loads, on the other hand, are calculated at 100% of their nameplate rating. Understanding the difference between these two types of loads is critical for accurate load calculations. In addition to the NEC, there may be other codes and standards that apply to electrical installations. These codes may be specific to your local jurisdiction or to the type of building you are working on. It is important to be familiar with all applicable codes and standards before starting any electrical work. For example, hospitals and other healthcare facilities have specific electrical requirements that are designed to protect patients and staff. These requirements may include the use of isolated power systems, redundant power supplies, and special grounding and bonding techniques. Industrial facilities also have specific electrical requirements that are designed to protect workers and equipment. These requirements may include the use of explosion-proof equipment, intrinsically safe circuits, and special grounding and bonding techniques. By understanding the applicable codes and standards, you can ensure that your electrical installation is safe and compliant. The NEC is updated every 3 years, so it is important to stay up to date on the latest changes. The NEC changes can be significant, and it is important to understand how they affect your work. You can stay up to date on the NEC changes by attending training courses, reading industry publications, and consulting with qualified electrical professionals. Furthermore, consider the impact of electric vehicle charging on the electrical system. Electric vehicles are becoming increasingly popular, and they can place a significant load on the electrical system. When installing an electric vehicle charger, it is important to perform a load calculation to ensure that the electrical system can handle the additional load. The NEC provides guidance on calculating the load for electric vehicle chargers. It is also important to consider the type of electric vehicle charger that you are installing. There are two main types of electric vehicle chargers: Level 1 chargers and Level 2 chargers. Level 1 chargers operate at 120 volts and can take up to 20 hours to fully charge an electric vehicle. Level 2 chargers operate at 208 volts or 240 volts and can fully charge an electric vehicle in a few hours. When selecting an electric vehicle charger, it is important to consider the charging speed, the voltage, and the amperage. Additionally, think about the coordination of overcurrent protection devices is another critical aspect of electrical system design. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. It is important to coordinate these devices so that the smallest overcurrent protection device trips first, isolating the fault and preventing damage to other parts of the electrical system. The NEC provides guidance on coordinating overcurrent protection devices. This guidance includes tables and formulas that can be used to calculate the appropriate size and type of overcurrent protection devices. Proper coordination of overcurrent protection devices is essential for ensuring the safety and reliability of the electrical system. In conclusion, when calculating ampacity for a duplex versus two dwelling units, it is important to follow the NEC and local codes. Be sure to perform accurate load calculations, apply the appropriate demand factors, and coordinate overcurrent protection devices. By following these steps, you can ensure that the electrical system is safe, reliable, and compliant. Remember to consult with qualified electrical professionals for any questions or concerns.